In this video, we're going to work through some of the practice problems for Unit 6, Day 6, which is working with projectile motion. So this is the main real-world application of quadratics that we're looking at in this unit. And let's work through these questions and see a couple of the things that I didn't specifically talk to you about in other lessons yet. Let's dive right into the question, and I'll explain what we need to know as we go. A rock is thrown up into the air, and the height of the rock in meters is represented by h equals -5t squared plus 21t plus 4. Hopefully you can see this in the video, otherwise just follow along with your own copy. Once again, this is Unit 6, Day 6, and I will have this posted to Classroom. First, let's talk about the form of the equation. I'm just going to write that down here. H equals, and this is going to be standard form. So we talked about the two forms of quadratic equations, vertex form and standard form. This is standard form, so I have an a, instead of x, they're using t, so at squared plus bt plus c. If that looks a little bit too different, usually we think about it like this. Y equals ax squared plus bx plus c. And we've talked about converting from vertex form into standard form. The only difference here is that our y value is height, so they just use h right away for height, and our x value represents time, so we're using a t right away for time. The a is going to represent acceleration due to gravity. So everywhere on Earth, everywhere in the universe, gravity is pulling at you. Specifically on Earth, it's a constant value. So gravity is always pulling us down. So I can predict, and we have measured, and we can predict how quickly and with how much force things get pulled down. So when we drop a pen or throw a ball or whatever, we can calculate that. So this value for all these projectile motion questions is always going to be -5. This is related to the fact that gravity accelerates things at a rate of 9.81 meters per second squared. So basically, it pulls things down at about 10 meters per second squared, and this is half that value. So this is a little bit rounded, but it's close enough for our purposes in math class. If you take a physics class, your teacher might have you use a slightly more accurate number, but this is fine. So our a value, you can even just think a for acceleration here, is -5. Our b value here represents our speed, so how quickly our ball is being thrown, or rock, or whatever we're dealing with. And finally, c represents our starting height. So maybe, if we throw a baseball, we're not throwing it from the ground, we're throwing it from the height of our hand, so 4, 5, 6 feet. Or in some questions, perhaps we're up on a building and throwing a ball off a ledge or something. That's what this number represents. So let's see that in action up here. Our equation was h equals -5t squared. So that -5 is the acceleration due to gravity. That's always going to be the same in all our questions on this sheet. Plus 21t. So 21 is our speed and 4 is our starting height. Let's take a look at our question, our units of measurement, and answer these. So A, what was the initial speed of the rock? So this is our initial speed right here. It's 21. And what is that measured in? Well, it's going to be our independent variable over our dependent variable over independent variable. We have meters and we have time. So it's going to be meters per second. It's a speed, so it has to be some unit of distance over some unit of time. So we know right away meters per second. Otherwise, think it's like the slope of our graph, and that's always the rise over the run. So the y value over the x value, or the meters over the seconds in this case. From what height was the rock initially released? That's our c value, our starting height. So our starting height is here. That's 4, and don't forget your units. It's meters. How high was the rock after 7 seconds? Well, sorry, after 4 seconds. What are we setting equal to 4? Our height or our time? Well, we need to find the height. We don't know what that is. We do know the time is equal to 4. So we're just going to take our equation and plug in 4 instead of t. So h equals -5 times 4 squared plus 21 times 4 plus 4. You might notice this looks familiar. We do this kind of thing every time we complete a table of values. I have my independent variable that I've chosen or been given in the question. I plug it into my equation, and I find the dependent variable, which is my y value. So I'm just going to use my calculator for this. -5 times 4 squared plus 21 times 4 plus 4 is 8. So how high was the rock after 4 seconds? The height was 8, don't forget your units, meters. And finally, we're asked to graph the height of the rock on the axis provided. So we're going to finish our table of values. We already found 1 point, so that's why I wrote that over there right away. Let's find the rest of the points. In each case, we're just going to write out our equation. Every time I see a t, I'm going to plug in the given t value I'm calculating for, and then write it in. I've done this enough times with you already. I'm not going to go over it again. I have a graphing calculator that allows me to make the whole table right away. So I'm just going to copy the values in. So when time is 0, the height is 4 seconds. When the time is 1 second, it's a height of 20 meters. At 2 seconds, it's at 26 meters. At 3 seconds, it's at 22 meters. And at 4 seconds, it is at 8 meters. Now that I have my table of values, I can graph. So when time is equal to 0, there's a height of 4. When time is equal to 1, we have a height of 20. Time is equal to 2, I have a height of 26. Time is equal to 3, I have a height of 22. Time is equal to time is equal to 4, I have a height of 8. And then connect that with a nice smooth curve. And we didn't actually calculate our x-intercept here. I don't know exactly what time it will land. We can just extrapolate for the sake of our graph and just finish up the shape. And that's all we had to do for this question. So a lot of things we've seen before, just we need to now know that there's a real world meaning to the A, the B, and the C value when we're talking about projectile motion. All right, I'm going to jump ahead to number 2. Jackie throws a baseball up in the air at a speed of 16 meters per second and releases it at a height of 2 meters. Determine the equation in standard form for the height of the ball. It's going to be that same general form. H equals A t squared plus bt plus c. We just need to figure out the values of a and b and c. So we said a is the acceleration. It's always going to be -5. And it's negative because things are getting pulled down toward the ground. The t is our variable, so t squared plus our speed. Our initial speed is 16 meters per second. And our c value released at a height of 2 meters. That's our starting height, plus 2. There we go. Didn't even need to do any calculations. We just had to recognize which number goes where. What is the height of the ball after 3 seconds? Well, we don't know the height. That's what we want to find. I do know the time is 3 seconds. So take our equation and set t equal to 3. So height is -5. 3 squared plus 16 times 3 plus 2. -5 times 3 squared plus 16 times 3 plus 2 gives us 5. Don't forget your units. So in the final answer, the height of the ball after 3 seconds is 5 meters. And that's it for number 2. Let's take a look at number 5, where we add an extra step into the process. A football is thrown in the air, and the maximum height of the football is 48 meters, and it occurs after 3 seconds. Determine the quadratic equation in Vertex form that calculates the height of the football. Let's sketch the situation roughly just to get a feel for what's happening. Height, time, football is thrown, and I know the vertex, that tip of my parabola, is at 3 seconds and a height of 48 meters. We've talked about this kind of thing before with transformations. So I'm going to have moved my peak of my graph over to the right by 3 units and up by 48. So what does a vertex form equation look like? It looks like this. Y equals a, x minus h squared plus k. We already know the a value. That's the same a value we had up here. So it's still the acceleration due to gravity. So it's just going to be -5. What's our h value? That's how far over we've moved on our graph. And we've moved over, the peak isn't at 0, 0. We've moved over 3 units. So h is going to have a value of 3, and k is how far up our peak is, and that's at 48. So we can even label that here, 3, 48. So our k value is 48. And that's kind of it. Let's just rewrite our equation. Height equals -5 bracket x minus 3. Remember, it moved to the right, so I should see a -3 here. It always does the opposite of what we expect. Plus our k value of 48. Okay, What is the height of the football after 4 seconds? Once again, we're going to plug that into our equation. Time equals 4. Height equals -5. Oops, sorry, I should have used a t here for time. It doesn't really matter, but just to try to be consistent, it doesn't really matter usually what letter you choose. All right, -5, we said t is equal to 4 minus 3 squared plus 48. I don't have a lot of room here, so I'm going to do it all in one step in my calculator. 4 minus 3 is 1 squared. I simplified. I can type out the whole thing, though. Height is 43 meters. All right. What was the initial height of the football when it was released? Normally, we can just look at our c value, but in this case, I don't have a c value. I have an h value and a k value. But what we do know is that initial means at the beginning, means when time is equal to 0. So I can just do the same calculation I've been doing, except this time I'm setting the time equal to 0. So let's write out our equation. When I get to the t, I'm going to put 0. Once again, we can do this all in our calculator. You can simplify a little bit, or you can just type it in like you see on the page. And 3. Therefore, the initial height of the football, or the height of the football when it was released, was 3 meters. Finally, let's take a look at number 7. A crumpled up math test is thrown into the air, and the maximum height of the test is 30 meters, and it occurs 2 meters after the test is thrown. Determine the quadratic equation in Vertex form that calculates the height of the math test. Same as our previous question, height equals our a value, which is always -5 for these kinds of questions. T is our time. It happened after 2 seconds, so that's how far the t is being offset, or how far to the left or right removed. We're going to -2 squared plus, how high up is our vertex? It's at 30 plus 30. And then we're asked to graph the height of the math test on the axis provided. So we're going to quickly make our table of values and calculate. So the times we're going to deal with are 0, 1, 2, 3, 4, 5 seconds. 0, 1, 2, 3, 4, 5. Let's calculate. I've done this calculation enough with you by now. You know that we just take the t value, plug it into the equation, and our answer is our dependent variable, our height. And then we do it again, take the equation, plug in the 1, and so on. Once again, my graphing calculator can do this a little bit more quickly. So I'm going to go ahead and use that instead of doing all the calculations step by step. Just double check I got my equation right. Looks good. I'm going to copy in my values. At time is 0, the height is 10. And 25, and 30, and 25, and 10, and -15. All right, let's put it on our graph. When time is 0, height is 10. At 1 second, we're at 25. At 2 seconds, we're at 30. At 3 seconds, we're at 25. At 4 seconds, we're at 10. And at 5 seconds, we're at -15. My graph doesn't extend that far, so I'm not going to worry about trying to extend it. It would look silly. This is depicting a real world situation, so we know the ball's going to stop when it hits the ground anyway. So, I mean, that would be down like here somewhere, so we can kind of backtrack, and looks like our x-intercept is right around there. Smoothly connect the dots. I've told you before, sometimes it helps to have a little horizontal line at your vertex, just to help your graph have a more correct shape. And that's not too bad. Looks pretty good. I hope that made sense. As always, if you have additional questions, please message me or post on Classroom, or if there's other homework questions you want me to go over, just let me know and I can even make another video. Happy studying.